We're going to be looking for the area of the region enclosed by one loop of the curve r is equal to sine 2 theta. So we're looking at a polar coordinates here. Now r is equal to 2 sine theta looks like this on the graph. One loop is going to be this little bit here. So we're looking at the curve between 0 and pi over 2. Now when we're looking at area, we know we need an equation for that. Our area equation in polar coordinates is the integral from a to b 1/2 r squared d theta. So that is what we are going to be using. I'm going to rewrite this once more because this is the shorthand that most everybody uses, but we can also read it as 1/2 of f of theta, because r is equal to f of theta, quantity squared d theta. So in other words, what we want to do is we want to get rid of the r's and think about it in terms of theta. So to do that, what we're going to do is instead of f of theta here, we're going to punch in sine of 2 theta. So we're just going to do a substitution right there. And then we look at our a and our b, and that is going to be 0 and pi over 2. So those are our little coordinates there. One thing that I will point out that we can do if we want to, in fact, I think we might do that just to make it a little bit easier to look at. We do have symmetry here. You'll notice that the half of our leaf that is underneath is the same as the half that is on the top. So in fact, if we wanted to, we could go from 0 to pi over 4 and just double it to get our entire area that we're looking for. So let's write it up. We're going to start with area is equal to, and let's put this back in black. We're going to 0 to pi over 2 of 1/2 r sine squared, not r, sine squared of 2 theta d theta. And we are going to use our little trick there. Right, this is 2 times 0 to pi over 4 because of symmetry. 1/2 sine squared 2 theta d theta. All right, now this tells us our 1/2 and our 2 can be canceled, and then we just have the sine squared 2 theta. So I'll write that out again. 0 to pi over 4 sine squared 2 theta d theta. Now off on the side here, when we have a sine squared of something, this is the same thing as 1 minus cosine of 2 theta divided by 2. I'll just put that off on the side. So we're going to do a replacement here. We are going to from 0 to pi over 4. And I'm just going to take that 2 and bring it out front. So we're just going to have a 1/2 1 minus cosine of, and notice in our formula here, we start off with a theta and we end up with a 2 theta in our cosine. In our particular integral, we start with a 2 theta, so we are going to end with a 4 theta inside of our cosine. So now we have 1/2 of the quantity 1 minus cosine 4 theta d theta. And we are ready to integrate that. Our integration of 1 is going to give us our theta. There's our antiderivative. And instead of cosine, we are going to get a sine of 4 theta. And we're going to divide out by 4 at the front to offset the 4 inside our parentheses there. Now, we could go through this step by step. That is a u substitution that we're actually using there. But if we go through and actually do the u substitution bit by bit, it is going to take a lot longer to finish the problem. So sometimes we can, if we know what we're doing, we can kind of just slide that in there. All right, so this gives us 1/2, and now we punch in our pi over 4 minus 1/2 of sine 4 times pi over 4. And then we subtract 0. When we put 0 in everything, we are going to get 0. So 0 minus 1/4 sine of 0. Okay, so all of this is equal to 0. Our 4's are going to cancel here, and sine of pi is equal to 0, so that vanishes, and that leaves us with a 1/2 and a pi over 4. So that is going to be 1/2 times pi over 4, which gives us pi over 8 as the area of one loop of the curve r is equal to sine of 2 theta. Thank you so much for listening.